example. Hello, everyone. Did you get my message that we're going to start a little late?
Yes.
All right, good. Sorry about that. Technical difficulties, but they have been resolved. Okay, how's everybody today?
Good.
The homework got figured out?
Yes.
Yes, okay. So, how was it in terms of like the amount of time that it took to solve?
Longer than expected.
Uh-oh. How long did it take you?
Well, I mean, I think it depends on how many steps you wanted to do or what you wanted to see. I mean, I was
Sure.
trying different things that I could use for my research as well. So that's why maybe it took longer than I expected in my personal case.
Okay. Anybody else wants to chime in? No? You have silently completed it and that's about it. Okay, you don't want to hear about it more. Excellent. Well, I'm gonna make a general comment is that 3D image analysis is not trivial. The moment you're working with three-dimensional arrays, it can get intense pretty quickly because your linear size is, for instance, nx by ny and by nz. Let's say that you have n cube of something. Your linear size, the problem often grows cubically with the linear size. And we always are chasing sort of like having this representativeness. You want a larger, as large of an image to analyze as possible. So it's very common to get into this pretty long, image analysis times for any problem. Now, the way, starting from segmentation onward, it's always a very good idea to isolate a much smaller problem. If you are about to analyze a large problem, then you analyze a smaller problem first, where you kind of can easily see everything that is going on, which is not always easy in porous materials. And then once you establish that you understand what you actually have, then you kind of move on to the larger problem. And again, yeah, establishing how many steps do I need? Well, before you do the analysis, you often don't know. So you gotta go through some of the steps first to basically just gauge and then move on to a larger problem. So always kind of isolate a small problem. Okay, without further ado, let me actually open my slides. And I am going to share my screen. We are going to go through network construction today, and we're going to do two things. I'm going to slightly skip ahead and then come back to some of the points made. One thing that I didn't ask you ahead of this, which is what we're going to need next time. Does everybody have MATLAB installed on their computer?
Yep.
Is there anybody who doesn't? So you have access to MATLAB through UT, so it shouldn't be a problem to install. We're going to have just some very ready-to-go examples to work with, which are going to be reminiscent more of just a standard petrophysics and are not necessarily image-based, but I have them for historical reasons. I have them in MATLAB, and I haven't translated them. I can point out to how to do things in Python, but it's just I'm going to give you the scripts to execute. Yeah? But we're not going to get to it today. I think I actually want to. Initially, I planned to do that first and then go to the network construction from images. But I think we're going to go through the image analysis part and then come back to this part because the exercise is really about looking into the relationship of permeability versus porosity and such, which is kind of petrophysics based on sphere packs, not based on images. So in any event, I'm getting ahead of myself, so I just wanted to verify. So if you don't have MATLAB for some reason on the machine you're using, please install it by next time using your UT privileges. Did I share? Share. There's my control. Okay. Do you see my screen?
Yes.
Okay.
Yeah.
Excellent. All right. So question is, I went through the historical overview of network models, and there's no doubt that having conceptualization of a complex flow in porous media using a network is a useful exercise. And it also relates in a lot of different cases. You could have a network on in your porous medium on your micron scale, but ultimately a pipeline is a network as well. You just have to apply different flux formulas on different scales, but concepts are it's rather easy to conceptualize and figure out how things in networks flow. So there's definite benefit of viewing your transport problem using network. Question is though, how do we obtain a representative network of a porous medium? Historically, there was the historical overview. This average pore concept started at the end of 19th century, 1899 by Dijkstra. And then it got developed, especially mid 20th century. But it's all nice and dandy if you actually have this magical average pore size to work with, or some sort of set of pore sizes, but how do you actually come up with a network is a very good question. And you can always come up with a network and draw one. We had those images by Fatt. Where are they? This is how networks by Irving Fatt looked like. So they were these regular lattices. They were beautiful, but are they actually representing a porous medium that you want them to represent, or bundle of tubes for that matter? So how do we get a network from, especially now, 1990s and onwards, we actually have images, very realistic images using microtomography. Can we actually figure out the network that is representative of that image? So let me move on. Okay, so basically in the very beginning, we had this bundle of tubes, and I call these simple networks. In the simplest of cases, you can create a structured network, which is either a bundle of non-intersecting tubes or some sort of regular lattice of interconnected tubes. And in a more complex case, you would like to create what's called unstructured pore-throat network. Connectivity of these tubes follows the actual porous medium. And those are what one would call a representative. And they can be built from analytical model of sphere packings, and that's one of the exercises that we're going to get to. I'm going to just explain it today. We're going to practice it next time. You can build them from a granular or an analytical model of a porous medium, but you could also use an image. And those are, again, what we call representative, and they're typically unstructured, so we have a pretty complex connectivity and spatial positions of these pores and throats. Okay, so what is the idea? We kept talking about pores and pore throats, and it's a very good question, how do you define one? So I'm going to go to a classic text of Jacob Baer, which in Dynamics of Fluids and Porous Media. So this is a classic textbook in hydrology, and that defines hydraulic radius of a fluid pathway. If you have a cross section of that pathway, its hydraulic radius is area divided by perimeter. Okay. Now, technically, what we refer to a throat is this pathway. So we're talking about cross section. So it's essentially a two-dimensional object that has minimum radius, hydraulic radius, along certain path, right? And pore is some sort of pore space opening enclosed by grains and throat surfaces. Okay? So if I have a simple medium, you have been accustomed to this small porous medium of mine, which is from that polyethylene image. So if I have, and you're actually looking in red at medial axis paths of that image. And technically, if I'm going along, so I see here sort of a larger pore opening, and there is a center. So here is where basically there's actually two medial axis branching points here within, but I can kind of assume this is just one. I can merge them together. And so this is my center of a pore or this opening. So I actually have a medial axis going from here along this sort of a narrow constriction. And basically what you see here in this, what is this color? Magenta. In the magenta color, there is a surface here or a line that has sort of the minimum, in this case, length. So technically, this is my tightest point, and this is where I would expect minimum hydraulic radius. So this is my throat right here. Now, throat, again, is a surface. It's not a tube in itself, but we conceptualize flow between this pore center and the neighboring pore center, or this one, or that one, as sort of a flow through a tube that has this minimum, this path constriction, okay? So this is my throat. Now, most of these throat finding algorithms, they don't necessarily go and minimize hydraulic radius. They don't find this cross-section and look at their area over perimeter, but they actually minimize just the area. And if shapes along a path are similar, that's actually a pretty good assumption that minimizing this cross-sectional area A is equivalent to minimizing throat radius. And there's a little bit of a mathematical derivation of this right there. But again, minimizing area and minimizing hydraulic radius is pretty similar. Now, this pore-throat view of a porous medium is not really well defined. It comes from sandstones, and in sandstones it's arguably applicable, but in a lot of media they don't come pre-packaged as pore-throat networks, so finding them is not always an easy thing. A typical algorithm will place a throat in between two pores, and here are some examples where you could be not so clear that there is actually a throat. So I'm going to start with the easiest one. Let's say that this is my porous medium, which is really just drawn. This is a paper from my PhD, everybody. Anyway, so there's a pore and there's another pore, and assume that my medium is this simple. Nobody will argue that this AB is a throat between this pore and that pore. Okay. Now, as you start opening up this AB portion, here it's still a throat. But as you near this case A, is this just a surface roughness that basically caused this to be a minimum? But if I look at the radius between, so this radius is not that much different from the radius of the pore itself. It's actually ever so slightly smaller, but not by much. And question is that a throat, or should I call it a throat, or should I merge these two things into one object? That's an open question. Again, there's nothing in the porous medium that really says where does one pore start and where does it end. Also, if I wanted to now, we can see, especially in this is not a tortuous path, but if it were a tortuous path, it's a question if I put a straight cylinder in between two pore centers. In this case, that straight path actually connects two pore centers. But if I actually am right here, let's look at one example, like here, this center, and that's actually pretty good. So this center and that center, you can see how if I put a straight path, I'm shortening the actual path that fluid is taking. So that's another issue. So if you replace this connection between this pore center and that pore center. If you replace it by a straight tube, you're straightening out the porous medium, and there are certain inertial effects that are lost. Okay, so those are the decisions that one has to make during the image analysis, which are not always clear how to make. Now, that said, from the point of like if you're just like draining this medium, and there's an interface coming through this, if I'm already in this pore and I'm coming through here, I'm just kind of gonna invade this entire space. So from the process of, from drainage standpoint, this is all one pore. Technically, even if my radii are not very different, I'm not gonna make really a mistake. I'm just gonna immediately invade, and this throat is not gonna stop the invasion. So in that sense, possibly it doesn't even matter how you define it, as long as the connectivity is correct. All right, so how do I construct these representative networks? So in pictures, basically, I have already shown you this imaged real media or real media. So I'm going to actually start from there. You start with the image, you segment it to decide where is solid, where is pore space. Medial axis is one of the ways. We're actually going to practice something way simpler, which seems to be the simplest and the most adopted approach right now, that is using watershed algorithm. And it's the simplest to apply. All of them ultimately have their little quirks. But technically, if I had this sort of a medial axis as a set of pathways, you could find these throats or the minimal constructions or the minimum constrictions. You can then place them almost like roadblocks in your medium, and then you acquire, so you can then define pores as bordered by solids and the throats. Okay, so this is one pore, this is another pore, this is the third pore, and so forth. So you have some sort of throat finding and partitioning of this pore space into the pore. Watershed algorithms, we're going to comment on how they do. They conceptually do something slightly different. Either way, you're supposed to end up with these pores and throat objects, and they neighbor each other and create a network. Now, after that, you can represent that network visually like this, where basically your pores are depicted as spheres and throat connections as cylindrical connections. Now, in model or granular media, you start with clearly identified grains, and then you go through a procedure called Delaunay tessellation that I'm going to explain, because it's a pretty powerful algorithm in computational geometry that is used for all kinds of analysis, and not just this. On one end, actually, a lot of tessellations of the space for reservoir simulation or any other simulations are done actually with tessellation algorithms. So it's something, it has applications in a wide-ranging set of problems. But here, what you do is you define closest throat, so in any packing, I have a neighboring grains. And in 3 dimensions, it is 4 neighboring grains that acts as center, that form a tetrahedron. And inside that tetrahedron, when you remove the spherical part, is 1 pore. And since this is a tetrahedron, it's a well-defined geometrical object. I can figure out what this volume is in between. I can figure out each throat now is the surface or a side of tetrahedron, and that's where my minimal cross section is. Okay, and then I still might have these problems of some pores needing to be merged. Actually, if you look really closely, you will see some of those were not removed prior to plotting this. So you will see actually these 2 spheres overlapping, and this is the spheres that overlap are the pores that possibly should have been merged as per the comment that I made before. But for visualization purposes, I just left them be. Okay, so this is basically the, in pictures, roughly how you go about finding a network. So there is, this is a slide that just provides the literature search of this started. So Fini packing is subset of the packing that we've been using actually for just analysis. In general, it's available on the DigitalRocks portal. Fini in 1970, at the time, there was no computer codes that actually pack spheres. Nowadays, that's actually a pretty common exercise to pack spheres in a box, just using a computer. Back in the day when that wasn't really available, he actually optically measured spherical packing, and 4,000 of those spheres are actually available on DigitalRocks portal. I contacted him and he agreed to post them. I had the access to those spheres through Professor Steve Bryant, who was my advisor back in the day. He used to be at UT Austin, now is at University of Calgary. And he got it from Fini back in the 80s or 90s, and he used it for a series of papers and one of the first representative networks of granular media. There is some other approaches as well that are way more complex, so they haven't really taken Fatt because of their complexity. I commented already on this explicit throat finding algorithms, and this is just a list of some of them. And then there are these algorithms that are called morphology-based algorithms, and we're going to actually use some of those because their implementation is easy. So we're going to experience some of this Delaunay tessellation and watershed-based pore partitioning because those are easier to grasp and easier to implement, and actually the algorithms are widely implemented. So let's just comment on how do I get this network from pore space using a spherical packing, or as long as I have really any kind of grains that are well defined, and we will comment on the methods that try to identify grains in images. So assuming I have a set of grains and their centers, and I can think about them as spheres, this is the method that would apply. So essentially, let's say that this is my packing of disks in this case, it's in 2D. So can you visually like look at the pore space? So I'm assuming I'm moving in between here. Can you visually just look and kind of try to identify where would be these constrictions and where are the pores? So if I asked you, hey, find the throats, what would be the easiest thing to do? What would you draw?
Maybe
Normally,
like
actually.
a line from the, like the center of two spheres. Like,
so here are the two spheres. Now what? This is a center, this is a center.
Yeah, and then like the perpendicular bisector or whatever. That would be the
line connecting them, right? And that's where the tightest spot is. That's precisely what the algorithm does. And that's actually what this Delaunay tessellation is about as an algorithm. So you take the centers, and these are now triangles. Note that this is actually immediately triangulation of set of points, regardless of where spheres are. We are interested in spheres because we are interested in pore spaces in between them. But in general, this is a general algorithm. When I have a set of points, okay, I connect them. So the three closest ones, I find the three closest ones, they define a triangle. And I keep going like that. And this is my set of triangles. And that set of triangles, that's called tessellation. It tessellates the space. It fills up the space. Okay. So if I needed these triangles to be part of my computational domain or define it, I could use them for that. Now, and because these spheres actually have radii around them, I'm not going to have a lot of, well, I should withdraw that comment. But as long as there's actually equal size, I'm not going to have very weird triangles. They're all going to be kind of well behaved. I will not have like triangles that are of a very oblate shape and so forth. Okay, great. So now I have this triangulation, which is called Delaunay tessellation. Any respectable computational environment has that algorithm available. That includes MATLAB, that includes Python, that includes C, like that algorithm was made available early and it's used widely. Okay, so you can find the algorithm that, given a set of centers, it's going to give you what those triangles are. And really what a triangle is, if you have a set of centers, it's a triplet of numbers or IDs that refer to those centers. So let's say that this is 1, 2, 3. Your first triangle is 1, 2, 3. And if this is a sphere 4, then your second triangle is 2, 3, 4, and so forth. Right? So sets of these triplets define a triangle. Now that's your pore. This triangle is a pore. This is a throat. You can figure out what this distance is. It's this distance minus 2 radii. So you have a throat measure right there. And in this case, it's a throat length. And basically, this pore space in between is one pore. And you can find the center of it because you're processing a triangle. It's easy to find the center. And it's right here. And this is your next pore. The connection between them gives you basically a connection where a fluid would go. Right? So you can also see this, what's called dual network. This is a center, this is a center of that triangle. The connection between those two centers is actually perpendicular through this line. So this dual is orthogonal to your Delaunay tessellation. And the dual is called Voronoi tessellation. So I can actually see that these red lines, that's the dual I'm talking about. And this dual, if I look at this, basically for all of the properties of this dual or Voronoi tessellation is that for all of the points in this Voronoi cell, it's 1, 2, 3, 4, 5 pentagon. All of the points inside this Voronoi pentagon are closest to this center. This center is the closest center out of all of these centers to any point in this pentagon. That's the geometrical property of a Voronoi cell. And then same goes for this. So this actually solves what's called in computational geometry post office problem. So technically, if you place a post office here, assuming you don't have any hills, and this is a very flat geographical region, then basically the post office here in the center is closest to any points over here. So if you were placing a post office, well, this is where it should go. Okay, so in any kind of a lot of this post office is one example. In a lot of distribution networks, it's an important problem to solve, these Voronoi cells. And here, they're just the dual. So this network of pores and throats, which is in red, is actually this dual network to the Delaunay tessellation. And I can use those. And again, they're widely available. What is the connectivity of each of my pores? So this is a pore, this here is a pore, this is its center. I can figure out how to inscribe a sphere inside. That could be one measure of a pore size. It's an underestimate, of course. So how many pores is each of these pores connected to? Anyone?
Equal to the amount of nodes that are connected.
Yes.
Down
So how
like
many
two
nodes
pores?
am I connected to these red lines? 1, 2, 3. Yes?
Yes.
So this one. 1, 2, 3. Again, 1, 2, 3. So if I don't decide to merge any, I could arguably, based on the discussion that I had before, I could maybe say, well, this is all really one pore, so I could just merge these two. Okay. Well, if you don't decide to merge, then all of them have 3 neighbors. Okay. So there's an average connectivity of the pore space, which is 3. Okay. Or this network, which is 3. Now, I'm going to move on from the exercise and I'm going to just explain. Well, I'm going to explain how it works, but we're going to do the exercise next time, because I would like to move on to the image just to get the greater appreciation for how these networks are obtained, and then we're going to flow through them. So if I have a sphere packing in 3 dimensions, I would actually take a tetrahedron. So I would take 3 spheres, okay? And I would find, so that this Delaunay tessellation works in 3 dimensions as well. It's just that you're going to work with tetrahedra. And as I explained again, like the closest 4 tetrahedra form, closest 4 centers form a tetrahedron. And within that tetrahedron, you have pore space. And again, using geometry, you can figure out what the size of that pore space is, what is the inscribed pore radius, and what are the connections to the other tetrahedra in this space. So this is the same type of reasoning that you would actually now apply from 2D to 3D. It's just harder to see in 3D. And again, you arrive at a network, and this is one example, a network visualized from this sphere packing, okay, from actually in a portion of the sphere packing. So how would I now get permeability through this network? I can flow fluid through this network of ducts, and this is something that we commented already. I need the measure of these radii. Typically, one way to measure is to just basically inscribe a sphere in between, and this is geometrical calculation that is rather easily done. So you can basically inscribe the sphere inside this pore, get the radius of this ball here, and you can also inscribe a circle in this. You're looking at the throat right here, and this one side is the throat, that is the smallest constriction, and you can inscribe a radius within as well, and that can be the radius of the tube you're flowing through. Okay, so then permeability, if you just use the very simple network where you would flow through cylindrical ducts, then based on the mass balance at each pore, you would essentially get a flow through. This is very similar to the exercise we did last time. So you just do mass balance at every node, which is here visualized as a sphere. Again, sphere here and sphere here, those are 2 different spheres. These are pores, these are grains. Okay? So at if I balance at every node, I will basically get a set of equations that I solve for pressures. And once I have that, then I just look at, for instance, all of the throats that are coming out to the outside, and look at their flux, and that gives me a total flux per this side, and then I need the area of it to figure out what the permeability is. Okay, so again, you get this. So this is just to kind of, it's hard to see, but this is a visualized the set of the tetrahedra based on this sphere packing. And in this particular case, since every tetrahedron has 4 sides, what is the connectivity in 3-dimensional space of this 3D network that you get from tessellation? I just told you. Everybody's sleepy today. How many neighbors do I have here? If my tetrahedron has 4 sides, and each side is a throat.
4 connectivity?
Yes, so my average connectivity is actually 4, which for sandstorms actually works pretty well. So there is uniform number of neighbors, which is 4, but the network itself is not structured. It doesn't have a clear lattice. This is not a simple lattice. It's not cubic. It doesn't have some sort of hexagons, triangles as a base. It's irregular. It's as irregular as these spheres are. So this is a dense packing, but it's actually in itself, it's irregular. Don't call it random, whatever you call it. It's, even though it appears randomized, because spheres actually have finite size. If you're thinking physically about packing them in a box, they're heavily correlated. There's nothing random about those positions because they're not supposed to intersect, right? Any kind of random set of points, you could throw them anywhere. These you can't throw anywhere. They cannot intersect, and therefore they're heavily correlated. So don't call this random. It's disordered, but it's not random. Okay. Now, and you cannot just get a packing by, again, throwing random points into a box and then giving them a certain radius. They're going to intersect. So there's no regularity in this network. It has sort of a doesn't have a specific crystalline structure to it, and so we refer to it as unstructured. Okay. So this is basically how it looks like if you cut through these tetrahedra. There's just sort of another depiction. So one thing that it keeps, this network, what it does well, it keeps the information how are pore spaces, how is pore spaces connected. Somewhat simplified, but it's actually pretty good. So actual connectivity and topology of the pore space is preserved. What it does wrong is that once you equip these estimates of the radii, of inscribed radii, are typically, if I just keep them as such without modification, that's too simplistic, so it's gonna typically underestimate the actual radii. Okay? Now, this is pretty good for the rocks that are actually have granular underlining. So if I'm actual granular medium, such as packing of sand, so anywhere in Gulf of Mexico, those reservoirs, there's a lot of reservoirs that are in unconsolidated sands. This is a good model. It's simplified. You want models to be somewhat simple. The actual calculations are simple as well. So that part works. The problem is estimating actual grain sizes and getting those grain sizes right. And does the Delaunay tessellation work well when I have a very variable grain size? And it does not necessarily have to work well. Now, not all rocks are dominated by grain structure, and a lot of carbonates are not, and this is not going to be a good model for carbonates in most cases. Second part of it is that I also need to be able to add cement. So this is going to be the calculation we're going to do next time. It's actual calculation of permeability through a network, and I'm going to skip it for now. We're going to actually use it as an example. And also what this enables is, in this sedimentary rock, we're going to grow cement on those spheres. Basically, the spheres allow for an easy manipulation, so you could cement them with uniform cement. And I'm saying cement is not real cement, and we don't know necessarily always how much to put, but that reduces porosity, also reduces connectivity. Some of those throats are going to be shut close. So that gives a simple numerical cementation experimentation, so you can actually see what is the influence of that cementation on permeability. And again, we're going to do that conceptual exercise next time. I'd like to just walk over the algorithms. So we're going to comment on all of these cases then. Okay. Ooh. Okay. So these simple models, sphere packings, they allow simple models of rock forming processes. And if you don't have an image, they're actually a very good way to go. What they also allow, since they're simple and analytically described models, they allow you to experiment much more than you can with an image. Image is typically image of a given rock. It's the way the rock is, for better or worse. So it's often hard to do what if kind of scenarios unless you have imaged a whole lot of them. So that's something to keep in mind. I personally, in my research, go back and forth. So I go back and forth, the simple models, the pore network models that allow easy experimentation, and those that are direct from images and are simply set the way images are, and you cannot always investigate a full range of possibilities unless you have done a whole lot of imaging. Okay, so they do provide insight. They have their, as any modeling, they provide a lot of insight, and it's important to know that from a lot of these analytically described models, that's basically where a lot of formulas we use come from, because again, there's a way to close them analytically sometimes, and that provides you with a closed form formula that you can generalize. Okay. So the limitations are that you have to have these green packings. So if you don't have a green packing that is representative of the rock that you want to study, they don't apply. If the rock is not dominated by grain structure, they don't apply. And this is where sort of the digital rock petrophysics and analysis of actual images, no matter what images are, comes in handy. Again, personally, my personal advice is always try to use multiple models. No model is actually perfect, so you have to kind of go back and forth different models. Okay, so this Delaunay tessellation is pretty elegant if you don't have any image and you just use simple model rocks. But if you actually have a sample that you can image, you could image, there's an entire line of work, and I don't have the citation here, but I can, I will provide you with a set of papers related to this. If you can basically do an SEM image that gives you approximations of where these spheres could be. So you can basically create realizations, or you can analyze spheres, your sandstone as a set of grains, and then model them and find their radii or approximations of the radii, and then model them as sphere packings. So that's always an option. Okay, so let's go to the image-based network construction, and I hope we get we might not even get to practice that today because the class got artificially shortened. So here's I'm just gonna, on one of these algorithms that explicitly look for throats, I'm just gonna explain it visually. We're not gonna practice them because they are, I have frankly gotten a lot of practice because there was not much, watersheds were not really developed, but or really easily and readily available for sandstones at the time when I was in graduate school. So I spent a lot of times analyzing results of these explicit throat finding algorithms. I think by now, watersheds and Maximal bowls are the ones that I use the most. I implemented this one, and there's a lot of things that I couldn't get out of it, so I didn't use it in my research. But they're easy to implement, and we're actually going to get an exercise in them. Ultimately, all of the algorithms are ever so slightly wrong for the reasons that I outlined at the beginning. So there's nothing wrong in using the ones that are easily implemented. But let me explain what happens with the throat algorithms. Let's assume you have a medial axis path, and there's a medial axis path extracted from a sandstone, and this is how it actually sits. This is a surface surrounding it. This is how it sits in the pore space. So you can actually see this is part of a sandstone that actually has a clear throat. So how would you search for that throat? Basically, there's one of the search algorithms that is implemented in 3DMA Rock. That's the software I worked with in graduate school. What it does, it starts dilating. And that's literally dilation algorithm that we talked about, this medial axis path. As I dilate, I will eventually touch a grain voxel. So when my dilation touches a grain voxel, it's going to grab that grain voxel and put it on the list. And it's going to keep going and add grain voxels as it puts them on the list. And then eventually, I'm going to fill up my pore space around this medial axis fully. And as I'm basically going around, every time I search those grain voxels actually here they're in this darker brown. So you can see red medial axis. And this darker brown are voxels, a subset of those voxels that actually form a minimum path, minimum length loop around medial axis. So this algorithm searches in 3D, which is not a thankless task. For these, as I'm adding these grains to the list, I'm searching for a loop, a complete loop around. If I find such a loop, and one such loop is shown here, I declare a throat. That's a throat. That throat is now sort of the severed polygon. It has a center in, at the medial axis. And you can see how these triangles are reaching to the center of these pore voxels. So basically, it's this sort of slightly out of shape polygon. It's not completely planar. It doesn't have to be planar. Things are rarely perfectly straight in digital world because they're digitized. So basically, it's this sort of planar surface, and I can get there its area. I can find its perimeter. And I can also fill up the space in between to grab a set of voxels that we are referring to as a throat. And that block of voxels is used as sort of a roadblock to define, to put roadblocks so you can define pores in the rest of the space. Okay? So this is how you search for one throat in this kind of a hand-wavy explanation. Now, this is an example of these, I call these throat barriers, these blocks of voxels that are in this case 6 connected in order to kind of block the space off so I can acquire where the pore voxels are. If you remember digital topology, they have to be 6 connected in order to kind of break down the pore space into disconnected portions. And you can now see this surface as a transparent pore, and there's a medial axis path within. So this is actually a coordination number for pore. So I have 1, 2, 3, 4 throats in 3D. And you can see these throat barriers in white and a medial axis inside of the pore to provide you with how the space looks like. Now, there's different other versions of this. There's another from Chatz's group in Canada. There's another algorithm that is looking for planar throats, again in digital space. Similar, what I would call a brute force search, going down the skeleton and taking paths of the medial axis or medial axis skeleton as the starting point for the search. So this is that point that I made, that medial axis is often used as a starting point of different types of searches in forest media because it reduces the complexity of the material. So, and that one is actually looking for the effective minimum hydraulic radius, okay? There's various simplifications. These are what's called brute force searches. They can take a long time. There are various speed ups. This is a speed up. This is a student who graduated ahead of me in my advisor was Brent Lindquist. So this just tries to be faster and basically shoot rays and see whether I can just find shortcuts to these surfaces in 3D. I'm not going to spend too much time. Ultimately, you arrive at some set of throats. The main problem in finding then pores, and there's a lot of inconsistencies because there is no clear one-to-one. So just just because you have found a throat, that doesn't mean that it's going to be used in your pore-throat network, because to define a pore, I have to have a clearly defined space that is completely enclosed in between these pores. And sometimes, if let's say that you miss finding one of these throats, say this one, for whatever reason, related to resolution and so forth, if you miss finding it, then you're going to sort of have a leak, and this pore will technically get merged with another. So there are errors there because you don't find a throat. And just because you started with the medial axis path as a search space, that doesn't mean that you're going to find the throat along every path. You might not find these voxels. So declaring what is a throat and finding it along every path is not a given. So that's something to be understood about these algorithms. And I had, frankly, in my half of my thesis was figuring out how to create Pore-throat networks for relatively open polyethylene sample that I pointed out that I've been using all along in this course. It's so open that it's often this definition of a throat doesn't make sense. So you simply don't find enough throats to define, and you have this, because of the digital errors, you have this merging of the pore spaces, and suddenly your entire pore space, or 80% of it, is in one pore, which is obviously not correct. So always finding separation of space into pores is, again, not a given, because porous materials don't think of themselves as pore-throat networks. It's a concept that we are trying to fit them into. Second point I'm going to make is that also not all porous materials have this pore-throat network is something that originated from granular media in sandstones, and that's where it's rather well applied. If you have pore spaces that are fibers, so fiber networks of various kinds are very open. So fiber networks will have 70 to 90% porosity. And as such, they're not going to be easily declared a pore-throat network, nor will any of these algorithms work for them. So the nature of the porous media does matter in how I define these. How do I go about actually searching for a pore-throat network? Now, back to our discussion of medial axis paths. So here you can see one example. So I rotated one pore along with its throat barriers. Throat barriers I made sort of like a see-through. They're not completely filling the space, just as a visualization exercise to kind of make them dominate the visualization less. And you can see how multiple branching points of medial axis paths, which are in blue, are within one pore, or what's found by pore-throat searching algorithms as a pore. So again, medial axis is not in itself a pore-throat network, and don't necessarily treat it as such. Okay, once you have a pore-throat network, however it is that you went around it, you can do various statistics on it, and that can serve as characterization of the medium, and it can basically be a basis for comparing to other media. So here is a distribution of pore volumes. This is log normal. So insights like this then allow me to say, okay, I have done this as a Berea sandstone statistics on the pore volumes, and I have found that roughly the distribution is log normal. If I wanted to create statistical representations, then I could use that type of characterization as a basis for essentially geostatistical analysis, and saying, okay, I can now create myself regular structure networks that have log normal pore volume distribution. Okay? And I can then claim that they're then representative of this Berea sandstone. Okay, so this type of characterization allows me to, for the cases where I don't want to do image analysis, to basically still do some representative analysis by using statistics obtained from real examples. This is surface areas. They're also somewhat log normal. It's pretty wide distribution. Effective throw radii often do this. So this is surface areas, whereas this is just effective throat radii means this is a radius where I assumed that my surface area is actually disc-like. So then I find the effective throat radius. Same with assuming a sphere for a pore radius, I get this skewed distributions. The when I look at the correlations, they're largely missing, which is an interesting point. So basically, when I look at the pore volumes and average pore volume of the neighboring pores, it's not correlated. Or if I look at the effective pore radii versus attached effective throat radii, we don't see a correlation either. So that's an interesting point. Okay. Now the second, this is one of the more used algorithms. It's called Maximal Balls algorithm, and it's very appealing from the algorithm point. What it does, it says as following: let's assume an inscribed radius inside for each point in space, and we can do that. We have, if you remember, that Euclidean distance field. That's essentially what it is. It's a field that has, for every pixel or voxel, it has a radius, and that radius is basically a radius of the maximum spheres that fits inside that pore space. Excellent. So basically, I can visualize my pore space as all of these intersecting spheres that I could draw. Okay. Now, so I have already set up those. Now, if I have, let's look at point A and B. A sphere that I place, or disk in this two-dimensional case, that I place here at point B, and sphere that I place at point A, they intersect. Okay? And as they intersect, since A is larger one, I'm gonna call it a master. And this B is technically, in these algorithms, it's called a slave, though I really don't like this master-slave designation. Okay? But subordinate. So B is subordinate of A. Okay? I can now recursively go and apply that. So basically, any smaller sphere here, as I'm going towards this is a throat, okay, will essentially be subordinate of B. And by that relationship, if you look at the parent-child relationship, technically any sphere along this stretch will be subordinate of A. Okay. Now, same thing will happen here at D. So technically, I'm gonna apply this recursively and find out that A is a master sphere in this entire neighborhood, and so is D. But when I compare A and D, they don't necessarily intersect. And because they don't intersect, I keep them separate. So they're not gonna be master or subordinate of each other. It's these master spheres that I, after processing this recursively, that I arrive at, that are my pore centers. And I find my throats is basically either there's, in this line of succession, A and its subordinates and D and its subordinates, there are two, there's a subordinate that is possibly subordinate of both of these, even though A and D don't intersect themselves. And that subordinate, or two of them, are essentially my throat. Okay, so I can figure out, I don't find throats very precisely, but I can figure out location where they are, and I can fit them in, and I can know certainly the inscribed radius of them. So this can be optimized. It's a type of a search algorithm that computer scientists work with a lot. And it was done, does any of you know Dr. Pacek? Yes or no?
No.
Former chair of our department before Dr. Olson, there was Dr. Pacek. So he was, when he did this algorithm together with Dr. Silin and now Dr. Jin, I think Professor Dr. Silin is in Shell and Godong is in Baker Hughes. So at that time, they were all at University of California, Berkeley, But Dr. Pacek was UT PGE chair for 6 years and is now chair of the department in KAUST in Saudi Arabia. So Saudi Arabia stole him from UT. So this is basically the procedure, and it's an algorithm that can be pretty quickly applied. So you can get a network and this topological relationships of pore-throats. So this is one example of these networks, and then some drainage curves that are borrowed from that paper. Okay, I'm going to, next one is the watershed. I'm going to, then we're gonna try it out. So I'm gonna, so that I don't start this pretty long discussion. Watershed algorithms basically partition, and they can partition either pore space or solid space. So in terms of pore space, I will get pore-throat network. In terms of solid space, I will get individual grains, and those we're going to try out in image J as part of the this exercise. So we're gonna again do that, and I guess the exercises that I mentioned in MATLAB next time. Okay. Sorry again for the late start today, but we're gonna continue on Monday. And by tonight, I'm going to get you your official grading of the write-up for midterm. Any questions? Did I put you to sleep effectively with all of these algorithms? Putting students to sleep is always a danger. When I don't see you in front of me, that's even more of a danger. But I hear one person laughing, so somebody is at least semi-awake.
Well, no questions yet, but maybe I think I'm still digesting the information before questions arise.
Yes, and I did throw at you actually a lot of different algorithms. So there's that Delaunay tessellation, maximal balls. I was about to start watersheds. All of those are actually pretty powerful computational geometry algorithms that you should remember the basics of just as conceptual ideas, because they can be modified to work for different purposes in image analysis or otherwise processing of three-dimensional data. So that's something to think about. They're not necessarily just tied to the application that I'm showing. They're generalizable and also very widely available, so you can use them for different other purposes. Okay, I'm gonna stop here, and I see you on on Monday. Stop video.